The demand for high-quality, large-scale products increased significantly in the last few years. Products of considerable size are often heavy and cumbersome and require longer setups and larger tools to be produced. This leads to higher manufacturing costs and longer lead times. Wire arc additive manufacturing, or Waam, is one of the additive manufacturing technologies allowing the production of large 3D metallic components by depositing material layer by layer. Very large parts in the order of meters can be 3D printed with Waam, which cannot be produced with any other additive technologies. Due to high deposition rate, the costs for Waam are much lower than powder-based variants, making this technology very attractive for many industrial applications.
At Huisman, we are constantly looking at alternatives to current used forgings and casting technologies. We have many unique and very large components in the order of 10 meters or even larger. Production of such components and guaranteeing their quality is challenging, expensive, and a very time-consuming process that can take several months or even a year. Waam can significantly simplify production routes, reduce lead times and allow us to produce locally, which is very crucial for our business.
But what is stopping us to move away from currently established technologies like casting, forging or machining and instead produce large products with Waam?
At Ramlab, we have managed to reach good process control via in-house developed process monitoring software. However, we are lacking a complete understanding of the relationship between the Waam process parameters, the formed microstructures and the resulting mechanical properties, which is essential in the production of high-quality products.
Today, most of the effort was on the Waam process itself, but very little attention has been paid to the internal structure and properties. AIM2XL innovation is to look from a materials point of view rather than from a process point of view on Waam. The program involves 6 closely related research projects at 4 universities addressing 3 major research lines: design and optimization, microstructure prediction and control, and microstructure mechanical property relationships. This involves the development of models capable of optimizing shape and properties for a target application, as well as models for process control to ensure that the design can be successfully manufactured.
AIM2XL is the first material-centric research program worldwide on direct metal deposition technologies, delivering fundamental knowledge on the relationship between processing conditions and the resulting Waam microstructures.
Successful technology development and transfer from the academic environment to the industrial floor requires close collaboration and interaction between universities and industry. AIM2Y, together with Ramlab, has established an innovation ecosystem that allows transferring the fundamental research performed at the universities to industry, right within one framework.
The AIM2XL consortium includes 4 academic and 19 industrial partners covering the whole knowledge and value chain. Leading Dutch universities, network partner, technology providers, material producers, equipment producers, software developers, testing and certification bodies, and end users in different market sectors, equipment, maritime, aerospace, oil and gas, components suppliers.
With AIM2XL, we get the chance to integrate our research in an industrial environment. The fundamental understanding and prediction of material behavior in relation to temperature distribution and process parameters we have verified on 3 industrial demonstrators.
The lifting lug is the first of 3 demonstrators produced within the AIM2XL program. Lugs are widely used in the maritime and aerospace applications as structural supports for pin connections or lifting. The optimized design of the part for the surface loads was realized by Waam and structurally tested.
Currently, the lugs are manufactured by milling from solid plates. This is a time-consuming and wasteful process. Adopting additive manufacturing technology allows more design freedom and more efficient raw materials usage.
The quality of large-scale metallic products is determined by the internal structure of the metal. During 3D printing, the material is deposited in small bits, which gives much better control over microstructure in comparison to traditional process such as casting. However, in order to fully benefit from the unique feature of 3D printing technology, we need to have a good control of the local process conditions and need to be able to predict the microstructure developed. Otherwise, we will have vastly different materials properties at different locations, resulting poor product qualities.
We identified the major process-related characteristics, such as spatially dependent grains, size and texture, using several advanced experimental techniques. We also developed a detailed micromechanical model to predict the macroscopic mechanical properties based on the characteristic microstructure. This experimental numerical approach provides an essential step forward in understanding the relationship between the microstructure and mechanical properties of wire arc additively manufactured components.
Designers often overlook the importance that print deposition strategy plays on microstructure and thus on the final 3D printed part. Multiple process-related factors control material responses, including metallurgical composition, the thermal-mechanical history, and the deposition direction of each deposited material bit.
At the University of Twente, we developed software to help us to optimize the process parameters and to obtain experience regarding the toolpath design and printability.
3D printed large-scale components often require grinding to obtain product final shape. Some applications may require quality surface finish, which involves both grinding and polishing. At RamLab, AIM2XL researchers also looked at a robotic system to automate the pre-cleaning and post-cleaning operations. The second demonstrator, produced within AIM2XL program, the fork, was designed to demonstrate and verify the influence local deposition path directions have on the resulting material properties.
A large-scale fork geometry consists of 3 beams that are printed with varying deposition patterns. The free ends of the beams are loaded with weights to generate bending. The elastoplastic bending response of the different beams is then used to validate the experimental and numerical findings of the AIM2XL program. For the production of the fork, we have used a software that was developed by the University of Twente to optimize the process parameters and to obtain experience regarding the toolpath design and the printability.
We have measured cooling rates at different locations during the printing process and helped to correlate the process parameters to the microstructural observations and properties. Excellent mechanical properties were achieved in the 3D printed fork with high ductility and mechanical strength in the final product.
The potential challenges in 3D printed metallic products are the thermally included distortions during the printing. The thermal and mechanical models developed within the AIM2XL program can help predict the degree of part distortions. This allows companies to take advantage of the new design freedom that Waam offers. This is showcased in the third and largest demonstrator produced within the program. An innovative rudder.
A ship rudder is an underwater blade that is used to steer a ship. Together with core stability fins, which are similar but fixed to the ship hull, we produce and install a few hundreds of these blades per year. And due to the profile and the curvature, it can be challenging to produce the desired shape, so there are always compromises. With the third demonstrator, we want to use the shape freedom that 3D printing gives and produce a better performing product. We are especially interested in the topology optimization procedure, which in this case helped us reach a 30% mass reduction compared to the original structure, while we still fulfill class and design rules. In the future, we can use the lessons we learned also for other critical components.
Rudder optimization integrates geometric features like crossing sections, hollow structure, and numerous challenges towards 3D metal printing, including topology optimization, performance, structural integrity, and potential add-up functions.
For this project, AIM2XL, we work together with TU Delft, who has developed a topology optimization algorithm that we use to optimize the toolpath for printing a 300+ kilo rudder that's going to be installed on one of Damon's boats. What we try to achieve is to create the same stiffness, the same structural properties, using a lot less material to print and a lot less waste.
We have shown that a topology optimized rudder can be printed with minor post-optimization alterations, but the biggest advantage is that we are now capable of producing optimized shapes to achieve high performance in a rudder.
AIM2XL program opens a new realm on how large-scale products will be made in the future. It also puts the Netherlands in a leading position for extra-large component production via Waam.